Hello, my name is Christopher and I'm a grad student at Carleton University, Canada, and today I'll be presenting our work by example synthesis of vector textures. By example texture synthesis is a long-studied problem where the user provides the algorithm with a small patch of a desired texture and the algorithm synthesizes more patches that resemble the exemplar without creating an exact copy. All of this work, however, has been in taking a raster exemplar and generating a raster result. Our goal, however, is to take a photorealistic raster exemplar and generate a purely vector result. And so why vector? The advantage of a vector format is with its resolution independence and editability and post-processing. But we'll talk about this a little bit more later on. And now we'll discuss some previous works. Many previous methods take raster exemplar and generate a raster result, and no current methods take a raster exemplar and generate a purely vector result. Li et al. Take a raster image and attempt to convert it to a vector format. However, these methods often rely on overlap and transparency, which makes their results lack semantic meaning and thus hard to edit. Other works like Tu et al. Take a simple distribution of already vectorized elements and mimic that distribution across the output canvas. And so our method works first by decomposing the exemplar into 3 layers. We then synthesize a new version of each layer and merge them together to get the final vector result. And so our contributions are to convert a natural raster texture into a vector representation. We then synthesize vector textures given our representation. And finally, we explore editing operations that are made possible through our vector format. And so our algorithm works first with an analysis phase, where we decompose the exemplar into 3 layers. In the synthesis phase, we create a new version of each layer. And finally, we merge the layers together to get our final result. We now look at our algorithm in a little bit more detail, starting with the exemplar, which is a user-provided raster image. In the first step of analysis, we extract the most prominent structures from the exemplar, and this is done using the segment anything model. We discard any textons that are too big or too small, and this creates our texton library. Next, we extract the secondary textons. This is the less prominent background detail. Any pixel not contained within a primary segment, we perform a passive flood fill segmentation. And again, we discard any textons that are too large or too small. The last step of analysis is with the background gradient. Any pixel that's not within a primary or secondary segment is clustered to get our color palette. Now that analysis is complete, we can move on to synthesis, starting with our primary texton layer, where we add primary textons to the canvas one by one, attempting to match the surrounding texton context. Next, we generate the secondary texton layer. This is done by sampling a Poisson disk distribution, and we place a randomly selected texton at each point. Now we generate the background gradient layer, and this is done by sampling a Poisson disk distribution. We assign each point a randomly selected palette entry, and we fill the background using radial basis function interpolation. Now that our layers are generated, we can merge them together to produce our final output image. And now we discuss some results. This first exemplar is ideal because it has a clear foreground background, there is no recognizable structures, and the texton distribution is stochastic. And as a result, we are able to produce a convincing output. As a reminder, all of our results are purely vector. When you perform a 4-time upscale, you can see the effect of the resolution independence. Note the sharper edges and interior detail in our vector upscale compared to a raster upscale. This next exemplar is tricky because there is highly recognizable expected structure, and despite this, we are able to capture the structure and produce a faithful result. This next exemplar is difficult because there is complex structure within the texton and complex relationships between the textons, for example, between the flowers and blades of grass. And even with these complex relationships, we're able to produce a faithful output. In the last example we'll show, there is no clear foreground or background, which makes it tricky for the segmentation, and yet we're able to produce a good result. However, it should be noted that these sorts of exemplars produce unpredictable results. We perform both qualitative and quantitative analysis with other state-of-the-art methods, but more details on this can be found in the paper. And now we discuss some vector edits made possible through our vector representation. In joint synthesis, the user provides an exemplar map, which tells the synthesizer which exemplar to sample from. On the left, we show something created with a simple mask from our map, and on the right, we show an example of our joint synthesis. If we zoom in, you'll see that our raster baseline cuts off textons, and there's a hard transition between the two texture areas. Whereas in our joint synthesis on the right, you can see smooth color transitions between the different regions, and there are no textons that are cut. Another application of our vector result is in vector interpolation. Since all of our textons are polygons, they can be moved, warped, and recolored into the textons of another exemplar. And so as a result, we're able to create a nice smooth interpolation between two exemplars. If you draw your attention to the vector interpolation, you'll see how these uniform circles are able to scatter and warp into the concrete texture. And now if you draw your attention to the raster crossfade, you'll see how these bubbles kind of fade in from the concrete, creating a less appealing result. Now we'll talk about some failure cases, starting with the low texton diversity. This case shows a failure of texton clustering, but tuning the parameters could make this exemplar work. In the center, we have a non-stationary input, which is a challenging case for any texture synthesis algorithm. And on the right, we have an exemplar with dense and large textons compared to the exemplar size. And so in conclusion, we synthesize vector textures. This is done in 3 layers: primary, secondary, and background gradient field. Our texture results are comparable with previous work while being purely vector, and we show how our vector representation has many applications. We also have a QR code which will take you to our project page, which has code and downloads, as well as a QR code that our algorithm attempted to generate, and a few other results. Thank you very much, and we'll now take some questions.